Our question today is, how are the scientific and everyday definition of work different? We use the idea of work all the time in our everyday experiences. Our everyday definition of work can be anything that's for mental or physical processes. A lot of times we talk about work as a job that we have to do. For example, you may go to work at a convenience store, or maybe you have to go to work at McDonald's. You might work as a lawyer, a doctor, a custodian, might be an accountant. And all these ideas can be either mental or physical. It could also be something like schoolwork. You have to do homework at home. That would be more of a mental thing. Or it could be yard work. You have to go outside and cut the grass. This would be a physical thing. In physics, it is a much more specific idea. Scientific work must be a physical process. And there must be two things that occur in order for scientific work to be done. First, you must apply a force. And second, the object must move a certain distance because of that force. So an idea of scientific work would be like cutting the grass. I'm exerting a force on the lawnmower, and the lawnmower is moving a distance because of that force. Another would be pushing your chair in after you're done, at your desk. So you're exerting a force on your chair, and the chair is moving because of that force. It might be something like raising a bucket, maybe out of a well. So you apply a force to the rope to lift the bucket, and the bucket moves because of that force. Now, if you push against something that is not moving, like if you push against a door that is closed, or if you push against a wall and it doesn't move, then no scientific work is done. You may be tired by the end, but no scientific work is done. If you were to hold up a heavy weight, maybe you have a 50-pound weight, maybe you have a heavy backpack that you're just holding. If it is not moving, you're not doing scientific work. So if you're just holding the backpack in your arms, you're not doing any scientific work, even though you may be exhausted at the end of this exercise. Also, there must be a force. So not only must there be the motion, but there must be a force as well. So if we have a rocket or a meteor, let's say, that's moving through space, let's say we have a meteorite and that's moving through space, there are no forces acting on the meteorite. It is simply hurtling through space because of inertia. And so no work would be done on the meteorite because there is no force. You must have a force and you must have motion in order for scientific work to be done. Now, work is measured in a unit called joules. It's named after scientist James Joule, and we usually abbreviate it with the letter J. Now, work can be positive or it can be negative. Work is positive when the object moves in the same direction of the force. This would be an idea of pushing something faster, like that lawnmower. You're pushing the lawnmower in the same direction that it's moving. Or when you raise the bucket of water up from the well, you're exerting an upward force and it moves upward because of that force. It's moving in the same direction as you're pulling. So those would be considered positive work. When you step on the accelerator of a car, you're doing positive work. The engine pushes the car forward and it moves forward. So anytime you speed up, you are going to be doing positive work. Negative work is when the force is in the opposite direction of the motion. This would be anything that you're bringing to a stop. When you apply the brakes on a car, the brakes apply a backward force, bringing the car to a stop, and that would be considered negative work. If you're pushing a shopping cart at the grocery store and you bring the shopping cart to a stop in order to put some groceries in it, that would be considered negative work because you are applying a backwards force to the cart, bringing it to a stop. Now, no work is done, though, if you carry the object, because in this case, the direction of the force is neither in the same direction of the motion nor the opposite direction. Instead, the force is perpendicular to the direction of the motion. So if this arrow D here represents the motion, If your force is perpendicular, like you're carrying an object, then scientifically, no work is done. So again, if the force is in the same direction as the motion, then that would be considered positive work. If the force is opposite the direction of the motion, in other words, bringing something to a stop, that is considered negative work. And if the force is perpendicular to the direction of the motion, in other words, carrying an object, that is considered zero work, at least scientifically. So what I want you to do is answer this question in your notes. Who does more work? A teacher lecturing to a class, or a mouse pushing cheese? So I want you to think about that answer. And then once you've written down your answer in your notes, I want you to unpause the video. So pause the video right now, answer that question, and when you're done answering the question, unpause the video, and then I want you to see how well you did. Okay, welcome back. You're supposed to answer the question, who does more work? The teacher lecturing to a class with a mouse pushing cheese. And the answer is, the mouse does more scientific work because it applies a force and moves the cheese. The teacher doesn't do any scientific work because there isn't a force or a movement from the teacher standing at the front of the room. Now what I'd like you to do is check your understanding of whether you know the difference between scientific work and everyday work by telling me, is scientific work done in the following scenarios? So a scientist delivers a speech to an audience of his peers. Next one, a bodybuilder lifting 350 pounds above his head. Next one, a mother carries her baby from room to room. The next one, a father pushes a baby carriage. And then the last one, a woman carries a 20-kilogram grocery bag to her car. I want you to write down which ones are scientific work in your notes, and then when you're ready, unpause the video, and then I want you to see how well you did. So go ahead and pause the video and state yes or no whether scientific work is done. And then when you're ready, unpause the video and see how well you did. Okay, welcome back. And the first one, a scientist delivers a speech to an audience of his peers. Now remember, you must have both force and motion in order for this scientific work to be done. And so in letter A, no force or movement is involved, so there's no scientific work. Letter B, a bodybuilder lifting 350 pounds above his head. So in this case, there is force and there is motion, so yes, scientific work is done. Letter C is a bit of a tricky question here. It says that a mother carries her baby from room to room. The key here is carries. And we had said in our notes here that when something is carried, no scientific work is done. Letter D, a father pushes a baby in a carriage. There is force and there is movement, and so yes, scientific work is done. And again, letter E, you have to be careful. The key word here is a woman carries a 20-kilogram grocery bag to her car. In this case, no, scientific work is not done because the bag of groceries is carried. Now to calculate work, we multiply the force and the distance. So here's kind of our formula. Work is force times distance. Force is measured in newtons, represented by the letter F. D is the distance measured in meters. And work is measured in joules. As long as we have things in newtons and meters, we measure work in joules, and that's the letter W. Now we want to calculate the work here in this situation, so we want to do a problem involving work. Here we have a man pushes a concrete block 10 meters with a force of 20 newtons. How much work has he done? So the first thing I want you to do is I want you to write down what does the 10 meters represent and what does the 20 newtons represent. I want you to write that down in your menu. So go ahead and pause the video, and when you're ready, unpause it and see if you have those two values correct. Okay, welcome back. Well, you should have what you should have is that the force is 20 newtons, the distance is 10 meters, and we're supposed to find the work. Now I want you to write down the equation. What are we going to do with the force and distance? Are we going to multiply or divide them? So I want you to write down your formula, and when you're ready, unpause and see how well you did. Okay, so you're supposed to write down what you're supposed to do with force and distance. They're beside each other in our formula, and so we're going to multiply them to calculate the work. At this point, I want you to calculate the actual work, so put in the values, your substitutions, and write your answer with your units. And when you're ready, you can unpause the video and see how you did. Okay, welcome back. You should have that 20 times 10, or the substitutions. When we multiply 20 by 10, we get 200, and the units are joules.